Welcome, dear students. The second class of numerical solution of linear equations. In the first class of numerical solution of linear equation, we had a discussion with Gauss elimination and Gauss Jacobi method. That those are the direct methods we have talked about. Now today we'll discuss about Gauss Jacobi iteration process mainly and Gauss-Seidel iteration. So in this chapter, we shall be concerned with the numerical computation of the solution of a system of n linear equations in n unknowns of the form 1.1. This system of equations is known to us. We had a discussion in the previous class also. These are the system of n linear equations in n unknowns, and where the coefficients aij and the constants bi are given numbers or in the matrix form notation. Now once again I want to repeat about the direct and iterative methods. Direct methods produce the exact solution after a finite number of steps. In these methods we can determine the total number of operations. These numbers is called the operational count of the method. Kramers rule, Gauss elimination method, these are the direct methods. And if on the contrary, if I talk about the iterative methods, are based on the idea of successive approximations. We start with an initial approximation to the solution vector and obtain the sequence of approximate x0, x1, etc., xk, etc., which in the limit as xk tends to infinity converge to the exact solution vector x. So this is the iterative methods. Now, in iterative methods, actually, we have an initial guess and we have to rearrange the equation. And also we'll see in the calculation of error, we will use the concept of norm vector, norm of a n vector. You know, norm of a vector is maximum over mod xi. So in Gauss Jacobi iteration, initially the given equations of the system are so rearranged that aii not equal to 0. That is a11. The leading coefficients are not equal to 0. And also the a22 not equal to 0, a33 not equal to 0, like this. So rearranged like that. And suppose that this rearranged system is 1.1. Now 1.1 is reset in the form x1 equal to 1 by a11 b1 minus a12. So you look at the equation, previous equation, this is your system, and suppose that a11 not equal to 0. Okay, then you can write x1 equal to, you are taking the rest of the terms on the transposing to the right. So that means b1 minus a12 x2 minus the other terms and dividing by a11, because a11 is not equal to 0. That will give you an equation of the type this one. 1 by a11 b1 minus a12 x2 minus a13 x3 minus etc. And similarly you will have x2 if a22 not equal to 0, x2 equal to this, and so on. And the last nth equation also you can write in this form. So this is the resetting of the equation 1.1. Or in brief you want to write, then you can write xi equal to 1 by aii bi summation j not equal to I, summation over j not equal to I, clearly mentioned, aij xj, I equal to 1 to n. Okay. So this is in brief. So you can write this. In the Gauss Jacobi method, the iteration is generated by the formula. This is k plus 1 is the iteration steps, xi k plus 1. I'm just writing, instead of this, I'm putting some iteration steps, that is k plus 1, 1 by aii, bi minus summation over j not equal to I, aij xj k, that is our iteration step, I equal to 1 to n. The initial guess xi0 I equal to 1 to n being chosen arbitrarily. That is the initial guess. So it will be given, you can choose it arbitrarily, it can be 0, you can start from 0.0005. Since we replace the complete x to the power k on the right, this one, on the right, this vector side of 1.4 at the end of each iteration, we replace this xj to the power k. This method is also known as method of simultaneous displacement. That is why this method is known as method of simultaneous displacement. So for the first iteration, you have to calculate all the values of xi. Then you substitute these values in the next iteration, and so on. To examine the convergence of the process, let k equal to maximum over I. In the numerator, you have summation j not equal to ai mod aij over mod aii, provided this k should be less than 1. We'll see that. So this is for examining the convergence of the process. We have to set like this. From 1.4, look at that 1.4. This is your equation 1.4. So from 1.4, for every I, we can calculate the epsilon error. Epsilon I k plus 1 equal to minus 1 by aii summation over j not equal to I aij epsilon j k. For at every step, you can calculate the error. And so if you take modulus, that is less than equal to 1 by mod aii summation j not equal to I modulus of aij epsilon j k, and that is less than equal to norm of the rest of the things are same, but you have a norm concept. You know that norm of n vector xi is denoted by norm x. Okay, this is the norm x. This is equal to actually maximum over I mod x, right? This is the concept of norm, and you know that norm x is greater or equal to 0. Norm of cx is c norm x. Norm of x plus y is less than equal to norm x plus norm y. This relation is also known to you. Norm of x plus y, this is norm vector, norm concept, less than equal to norm of x plus norm of y. Okay, so these are the concept, previous concept. So when applying that, you are getting this type of relations. Norm of epsilon k plus 1 less than equal to k, norm of epsilon k. Hence for every k, norm of epsilon k less than equal to k to the power small k, epsilon 0. This shows that if k less than 1, this norm of epsilon k tends to 0 as k tends to infinity. That is the iteration convergence. And what is the condition of convergence? K less than 1. And what is your k? K is this one. If this is less than 1, that means mod aii should be greater than summation j not equal to summation over j not equal to aii. This is called diagonally dominant property. This is called diagonally dominant property. So this is the important condition for the convergence. So look at that, the system of linear equations 1.1 or its coefficient matrix A is said to be strictly diagonally dominant if this holds. That is if k less than 1. Okay. Thus the Gauss Jacobi iteration converges if the given system of linear equations is strictly dominant. And you can calculate the error, estimation of error from this relation 1.6. You have norm of epsilon k plus 1 less than equal to k epsilon k plus 1 h is the step length, and that is less than equal to norm of epsilon k plus 1 plus norm of hk. And from here you can calculate the error. This is the estimation of error 1.9 will give you the estimation of error. Norm of epsilon k plus 1 less than equal to k by 1 minus k, norm of hk. Okay, so in the Gauss Jacobi method, we have described the method, also under what condition that a method converges, that is strictly diagonally dominant, or k less than 1, and k is defined in the process, and also you can calculate the estimation of error. Now we have some remarks. Equation 1.6 shows that here the convergence of iteration is of the first order. Okay, and it is clear from 1.7 that smaller is the value of the constant k, more rapid will be the convergence. So if you have a much smaller value of k, the convergence of that process or system will be very fast. Also note that the above condition of convergence is sufficient but not necessary. This is very important. Sufficient but not necessary. Okay, the condition, that is the k less than 1, is sufficient but not necessary. Without satisfying the condition, the system can converge. So this is sufficient but not necessary. Also, remarks number 2, the system of equations 1.3. Let me show you once again. What is your 1.3? Yeah, this one. Xi is a function of xj. You look at that, your right hand side is a function of xj, and this is xi. Xi is a function of xj. So from 1.3 is of the form x is a function of gx, x vector, where g is a n vector valued function of n vector variable x, and g is a mapping from n-dimensional vector space to real vector space to n-dimensional real vector space, Rn to Rn. This means that the solution x is a fixed point of the mapping G. Okay, this is a very important concept. Thus, the Gauss Jacobi iteration is a case of fixed point iteration because of this. So these are the very important note you have. If the k is very small, convergence will be very fast, and the condition of convergence is sufficient but not necessary. And Gauss Jacobi iteration is a case of the fixed point iteration because it is a mapping from R to the power n to R to the power n. Real vector space of dimension n to real vector space of dimension is n. Now let's come to express or explain the method Gauss-Seidel iteration. Initially, the given equations of the system are so rearranged that AII not equal to 0 is similar to Gauss Jacobi iteration. And suppose that is rearranged system is obviously 1.1, and now 1.1 is reset in the form 2.1. This is similar to Gauss Jacobi. This is the way we have expressed, because a11 not equal to 0, a22 not equal to 0, ann not equal to 0. This is similar. But you look at that iteration carried out successively by the formula x1 k plus 1, and on the right you have x2 to the power k, iteration stage x3 to the power k, xn k, k is the iteration stage, but you have calculated x1 k plus 1 in the previous step, that you can use here in the next equation, not in the next iteration. You can use the previous value of x1 to the power k plus 1, that is the improved value of x1 k plus 1 in the next equation, and you can use the x2 to the power k plus 1 as well as x2 to the power k plus 1 in the next equation. So in the first iteration, you can use the previous values of improved values of the variables in the next equation, successive equations. So this is the difference between Gauss Jacobi and Gauss-Seidel iteration. Or in brief, you can write in these notations: bi 1 by xn k plus 1 equal xi, sorry, it will be I. Yeah, xi k plus 1 equal to 1 by aii bi minus summation j less than I aij xj k plus 1 minus summation over j greater than I aij xj k. This can be written in these notations also. This system, and the initial guess is xi not being arbitrary. So that is the difference. You can use the improved values in the just next equation, but in the Gauss Jacobi method, you can use the improved values in the next iteration, not in that iteration. So Gauss Seidel is more fast to converge, is faster than the Gauss Jacobi method iteration. So if nothing is mentioned in the problem, you can use Gauss Seidel iteration. And also the conditions are same. This iteration will converges if k less than 1 and k is defined as this. Already we defined in Gauss Jacobi. So this is the same, and you can calculate the error. Similarly, you can calculate the error epsilon ik plus 1, and also the error equation. You can calculate the error equation like the same process. You have to do it like this. So this is also important, the error equation, estimation of error. In this case also having the same form. This is the error equation. Here also the condition, let us have some condition that the given system is strictly diagonally dominant. The same thing here is sufficient, and the condition is sufficient for convergence of the method, but it is not necessary, just like the Gauss Jacobi method. So it is also strictly diagonally dominant, that is AII greater than summation mod Aij I not equal to j. Okay, that was the condition, that was the diagonally dominant conditions. Yeah, summation j I equal to 1 to n AII, this is the diagonally dominant condition, and this is this condition is necessary but not sufficient. Sorry, sufficient but not necessary. Okay, and so the conditions are same, similar, k less than 1, or this is diagonally dominant. Now let's solve a problem on that. Now solve the system of equations using the Jacobi iteration method. I'm using Jacobi iteration, or you can do the problem by using Gauss-Seidel method, using the initial approximation xi equal to 0. This should be like this: I equal to 1 2 3, that is x1 equal to 0, x2 equal to 0, x3 equal to 0. So first of all, you have to check the condition, that is it is diagonally dominant or not. So look at that, of all the coefficients of x1 x2 x3 in the first equation, x1 has the greater magnitude, coefficient of x1 is greater, so 4 is greater than other, right? Other coefficients. Magnitude of x1, we will see the magnitude modulus value. And in the second equation, let's come to the second equation, you see the coefficient a. So in the first case you have a11 greater than the other, that is a12 and a13, right? Magnitude of a11 is more than their values. And also that is summation. Here you have a summation, so you have a plus sign also. I not equal j not equal to I. Okay, and this is in summation, so you have a sum of these values should be less than that 4. So sum of this, always remember. And also the second case, 5, that is the coefficient of x2, that is a22, modulus of a22 must be greater than the sum of these two values. Okay, that is mentioned here. You look at the diagonal dominant conditions once again. Yeah, that is the condition, summation j not equal to I, so you have to take the sum of the other coefficients on in that equation. So a22 must be greater than, and also you have a33, so this is your a22 is 5 and a33 is 3, right? So this is strictly diagonally dominant. Okay, diagonally you have a greater magnitude than the sum of the others. Okay, so it's diagonally dominant. Now using that, you have the iteration steps you can take. You can write the first equation. You can write the first equation as, let me write the first equation here. You can write the first equation as 1 by 4 2 minus, this is a simple equation, x3. Okay, you can write the second equation as x2 equal to 1 by 5 minus 6 minus x1 minus 2x3. Okay, and the last one. So this is how you can write. So 1 by 4 is 0.25, and x1 you can write iteration steps x1k plus 1. So you look at that, x2k, x3k, and x2k plus 1. Next equation, you see this is Gauss Jacobi. So you cannot use this improved value here in the second equation. This is your one iteration. So x2k plus 1 can be written like this. x3k plus 1 is, if you calculate, this will be like this. And your initial values approximations are x1 0 is 0, x2 0 is 0, x3 0 is 0. Now you substitute. So if you replace k by 0, then you have, if you replace k by 0, then you have x1 1, the first iteration. You are calculating the first iteration. Okay, first iteration, you can write it is as first iteration. So x1 1 equal to 0.25. I'm writing. So just try to understand the one problem. You can solve the problems by yourself. So it will be 0 minus, because k is 0 initially, so it is 0. So you are substituting these values and calculate. Then you can calculate x2 1, 0.2 minus 6 minus x1 0 and minus 2x3 0. Okay, you are not using the improved values in the second equation, but after the first iteration we can calculate the improved values. That is how. So this is the first iteration. Look at that, it is written first iteration. All are in terms of zeros, and you are getting on the left, you have x1 1, x2 1, x3 1, first iteration. Now I will write the second iteration. How? I will write x1 2, this is the second iteration, and your right hand side will be, let me show you, 2 minus x2 1. So I will use now first iteration. From the values of the first iteration I can substitute, successively substitute. Okay, and this is the process. Now x2 1 will be x2 2, sorry, second iteration. So 0.2 and minus 6 minus x1 1 minus 2 x3 1. Okay, and you have minus 1.2 if you calculate. Sorry, this is not 1.3, you have to calculate that. And you can write the third equation, x3 3, x3 2, sorry, x3 2 will be, you substitute and you will get the, so this is your second iteration. So let us see the second iteration. Yes, you have the second iteration like this, and you have the values. So you are using the values from the first iteration, improved values in the first iteration, in the second iteration. And in Gauss-Seidel, you will directly use this value of improved iteration in the next equation, in the first iteration only. So let me write here, let me compare here. So this is your first iteration. Okay, this is your first iteration. So in the Gauss-Seidel, the first iteration will be, your first equation will be same, no problem, 0.25, this is 0.25, 2 minus x2 1, sorry, this is your x2 0, okay, minus x3 naught. Okay, that is fine, you are using. But if you write x2 1, this is the process of Gauss-Seidel. This is your Seidel, Gauss-Seidel. If you are using Gauss-Seidel iteration, then it will be what was your equation? 0.2, okay, minus 6, okay, minus x1 1. I'm writing x1 1, and x3 is, you are not getting the improved value of x3, so you have to write 2x3 not. Okay, so look at that, I am using the improved value. I am using the improved value from the first equation. So immediately in the second equation we can use the improved value of x1, but that is not possible in Gauss Jacobi iteration. So that is why it is more convenient. Seidel is a more practical, that makes sense actually. You have a sense in that calculation, and it is more faster convergence it has. So that is the difference between Gauss-Seidel and Gauss Jacobi. So let's give you the second iteration. These are the values in the second iteration. Look at that. I am using the values from the first iteration. All the values of x1, x2, x3 substituted from the first iteration. Then in the third iteration, you have to go for the values from the second iteration. Okay? So on. And this interesting to note that the iterations oscillate and converge to the exact solution, but you will need a lot of steps. Large number of steps are required sometimes. So that is eliminated in Seidel because it is more practical. That makes sense that you are using the improved values in the second calculations. And lastly, I will say about the disadvantage of the Gauss Jacobi method. Already explained that disadvantage. At any iteration step, the value of the first variable x1 is obtained using the values of the previous iteration. The value of the second variable x2 is also obtained using the values of the previous iteration, even though the updated value of x1 is available. In general, at every stage in the iteration, values of the previous iteration are used, even though the updated values of previous variables are available. So this is the disadvantage. But in computing the values of the variable xi, we obtain a new method called Gauss-Seidel iteration, in where we could use the improved values. And in both the Gauss Jacobi and Gauss-Seidel methods converge, and then Gauss-Seidel method converges at least 2 times faster than the Gauss Jacobi method. Okay, so that's all my lecture today. In this lecture we had a discussion with beautiful discussions with the iteration process mainly, and the previous class we had a discussions with the direct method, that is Gauss elimination, Kemmer's rule, like this. This is the Seidel iterations process, and also we have compared that which one is better, and the conditions, error equation, also with a problem. You could solve some problems from your book. Okay, so that's all for today. Thank you all of you.